usually in some versions of the test, people will be given a picture like this, and people will be asked, are you given these pressures, and using an arrow, show me the direction of these specific pressures. You already know this. You know what hydrostatic pressure means, right? Hydrostatic pushes out. So when we say glomerular blood hydrostatic pressure, that's the pressure that's pushing substances out into the capsule. See? When you say capsular hydrostatic pressure, that's the one that's pushing pushing from the capsule back into the glomerulus. See? Hydrostatic, right? And then the osmotic pressure is the one that sucks it back in. So look at blood colloid osmotic pressure, go back in there. That's the pressure from the colloid or the proteins here that sucks it back in there. Okay? So you're going to be asked to compute. So the net filtration pressure is the glomerular. So the pressure's out minus the pressure going in. The pressure out is from the glomerulus, and then the pressure going in is this capsular and the blood colloid. So GB HP minus CHP minus blood colloid is 10 millimeters mercury. This is the normal value for all of us at all times if we are healthy. We cannot afford for that even to increase just 1 millimeter. It's going to push it very quickly. Or to go down, you're not going to form urine. So which means if you didn't get rid during the first trip, the next trip it will be even dirtier. Or what's returning is already dirty. Then you add more dirt. You cannot afford that. Okay? And that's why it's very important for us to always drink our water. You see? We don't drink water, it even affects your learning, everything. Now, so you understand how to compute? Very easy, right? That's the first step. This is the most important step in forming urine. You want to filter out. Once you get to this part right here, you just reabsorb, no problem. But this is the most important step, glomerular filtration. Blood pressure is the key. That's why we cannot afford to have either high blood pressure, low blood pressure. We need to maintain this magic number 10. Now, let's look at what is in the blood. Let's remember what's in the blood, right? You have your RBC, right? White blood cell, your platelets, your albumin, your globulin, fibrinogen, plus my water, my waste. The most common waste product from protein breakdown is called urea. You remember? The ammonia converted to urea, then go to the kidneys. Because ammonia, in ammonia form, is toxic. Remember that? Right? So this is really the main pain in the butt that we want to get rid of. The more protein we take, the more urine output we will have. So if you have a big steak or lots of chicken, drink lots of water. Drink lots of water to get rid of that one. Or well, not to get rid. You will get rid of that one. You will be dehydrated if you don't drink. And if you go to the buffet, just like I love going to the buffet, sometimes I forget to drink water because I'm just so obsessed with eating. Then I feel thirsty. Why do you feel thirsty? Because then you're getting rid of that. You understand? What? Look at. Then let's look at. There's also your glucose, your nutrients, right? Your amino acids, your fatty acids. They're in the blood that's flowing here. Do you remember our rule? I said, as a rule, in any blood vessel in your cardiovascular system, everything is able to leave your capillaries except this, right? Except your RBC, platelets, your WBC, your albumin, your globulin, fibrinogen. But everything else is able to leave your circulation. That's the same thing here. So here, when you get to the glomerulus, the glomerular filtration filtered out, yes, my urea, but it also filtered out my water, right? My nutrients, I'm going to write it as nutrients. My vitamins, maybe I took vitamins. Everything ends up in my tubules. That's part of what you call the filtrate. Because the only ones, as a rule, that are too big, they cannot escape my capillaries, is this. You know what this means, right? And they ended up here, you see. So we have to reabsorb them. That's why. Look at, because everything got dumped there. Everything is there. You have to reabsorb. Now, does it make sense that look at these convolutions, all of that, giving you time to reabsorb them? You understand? See? It's very easy. Very easy. But now, oh, that's why, look at this picture again. If we look at this picture, it keeps going, right? Your RBC, your platelets, your white blood cells, your albumin, globulin, fibrinogen. So here's my glucose. Here's my amino acids, fatty acids. There's my big waste, plus my toxic substances that I want to get rid of. I have my vitamins, hormones, water, everything that I want to reabsorb. How will you reabsorb them from the tubules? You remember that the tubules is just epithelium. Don't forget this. In your blood pressure helps us. Push, 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 squeeze it out. Blood pressure helps in your blood. But does blood pressure help you with the tubules? No. This is not cardiovascular system. There's no pressure gradient here. This is why this albumin is very important. But the albumin can only suck or reabsorb whatever is here in the interstitial fluid. How? The question is, how can I move these substances from here to here? I cannot squeeze it out. Blood pressure is not a factor here because this is not cardiovascular system. You understand? This is where we appreciate the importance of what you call pressure gradient. No. Concentration gradient difference. You see, we just always follow the law of physics. Do you agree? Look at, once I have filtered out everything landed in this capsule. As it moves in this part right here called the proximal convoluted tubule, it will make sense. It's so concentrated here. All the nutrients are super concentrated here, right? Right? Because I filtered them out, very concentrated here, yes? So, move down, diffusion. It will just easily move down by diffusion, right? There is something very important that we need to appreciate. This is why even when we're not doing anything, we get tired. You remember your muscles. Remember, even when your muscle is not contracting, you need energy for the myosin to maintain its cocked position. Look at your kidneys. Even though we're not doing anything, the kidney needs energy for that reabsorption to happen. Okay? You remember, look at your picture over here. So this is the the lumen? This is the peritubular fluid. There's your interstitial fluid. And there's your blood vessel, the peritubular capillary. This one, see, albumin, no problem right here to reabsorb. But you need to send the substances here to this part first. So here, we know that as it goes down, it's very concentrated, very concentrated. You can reabsorb them, but then it gets concentrated here, right? The problem is sodium is always, you remember, sodium is the most abundant cation outside. So if you're already starting with an abundant sodium here, it's going to be very difficult to push this, right? How do you do that? Active transport. See, it's ATP driven. Does it make sense? You remember sodium is always abundant outside, potassium inside. So and most of the reabsorption follows sodium. This is the one. The glucose just rides on a sodium bus. Urea, the same thing. So we look at, all books always look at sodium, how is it reabsorbed. So if this one, no problem. It's very concentrated, you filtered it out. So it's just going to move down by diffusion and enter here. I have a problem. How am I going to push it here to here when it's already concentrated with sodium here? You do so. You still do it by active transport, going against the concentration gradient, going against the natural tendency. You require energy. See? That's why even if you're just a couch potato, like my my dear honey, he still gets tired, you see. Even though we're just plain just sitting down, or maybe the old people, they still get hungry. Why? It takes a lot of energy to just be alive. You understand? Now, let's look at the ways that we reabsorb substances. The reabsorption, the route can be what you call paracellular. It can be reabsorbed in between cells or through the apical surface, through the cell, and then the basal surface. That's what you call transcellular. So either paracellular or transcellular. You will notice with the tubules, look at the polarity, right? That's why you say apical surface base. They all look different. Now you see with the tubules, it's the same thing as your GI tract, how there's villi, microvilli, and the function of this is to increase the surface area. Because you want to reabsorb, because really, each round trip, everything got dumped here. Everything except for RBC, white blood cell platelets, albumin, globulin, fibrinogen. And just like my common term, the bus keeps moving, you want to reabsorb. Hence, you have this microvilli of these cells that line your tubules. Okay? Now, we understand how we reabsorb right here in the proximal convoluted tubule. Gonna go back to this picture. It's very easy how we reabsorb in this first part. In this first part, I know diffusion plays a big role because I reabsorb, it is super concentrated here, right? Super concentrated. I reabsorb it. But by the time it goes to this part right here, how can I reabsorb? I'm sure the concentration here is no longer going to facilitate that movement from here to here, right? By the time you get to this part, I have already reabsorbed most of my solutes. This one is not too concentrated. And yet, there will still be nutrients that I want to reabsorb here in this part. You understand so far? So, how are we going to reabsorb them? Remember, we do not have pressure. You can't, it doesn't constrict, it's just epithelium. Here comes what you call uh, permeability differences. Okay? When you get to the loop, this is called the loop of Henry. This is loop. See, the loop has two parts, a descending limb and an ascending limb. And when you get to the loop, right here, see, here in the proximal, no problem, I reabsorb, no problem. But then here, my solutes will no longer be concentrated. It's going to be hard to reabsorb them. But they have a difference in permeability. Do you notice right here? This is the descending limb of the loop of Henle. This is the ascending limb. You notice this is reabsorbing water. This is not reabsorbing water. So this descending limb is permeable to water but not salt. This is always permeable to salt but not water. Isn't that amazing? And look at, how is water going to move? Well, I reabsorb all my nutrients here. So that means here in the interstitium is concentrated. And that's how you pull the water out. But the nutrients or the solutes cannot move. And so that's how you maintain concentration gradient. So it still stays concentrated. You see? Unbelievable. Is pressure involved? No. Because this is only epithelium. It's not blood vessel. But it's amazing how there's permeability differences. So water moves here. Water, by the way, moves through channels called aquaporins. Aquaporins. So aqua for water, pores for water. Okay. So this type of water reabsorption here in the descending limb is called obligatory water reabsorption. Obligatory water reabsorption. It's obligated because there's water channels there. It has no choice. It just moves down. It moves down by what? Osmosis. One more time. I reabsorb the nutrients here. And here in the proximal convoluted tube is very obvious. Diffusion. Because it's very concentrated. I filtered out everything. It's just going to move down here. Then, when you get down here, this one is impermeable to the rest of the solutes that stays here, but permeable to water. Water will move by osmosis because you have a concentrated interstitial fluid here from what you reabsorb up there. Amazing. And that's how you create concentration here. You're still able to maintain concentration here. So by the time you get to the ascending limb, it's very concentrated. And look at, the ascending limb is impermeable to water, but permeable to salt. And it moves by diffusion. So here, osmosis, here, diffusion. Was there contraction that happened? No, because it is not blood vessel. I'm just so amazed when I get to this part. How God is able to do that. Amazing. Then look at this one over here. Okay? Here is where sometimes you're going to have dark pee-pee, sometimes you have the light-colored pee-pee. It depends on your degree of hydration. So this part right here called the distal convoluted tubule, then you have the collecting ducts. Compare this with this one. Normally, no water channels called aquaporins normally. When you're dehydrated, all of a sudden, you're gonna, not all of a sudden, when you're dehydrated, you, your pituitary secretes antidiuretic hormone, remember that? And that antidiuretic hormone, remember we say the target is the kidney to conserve water. Here is where antidiuretic hormone comes into play, right here. So when you're dehydrated, you need to conserve PP, or no, you need to conserve water. So what happens is antidiuretic hormone is released by my pituitary. It goes right here. It tells the cells of your distal convoluted tubule all the way to the collecting ducts to what? Make aquaporins. So that you can move the water from here to here. By what? By osmosis. How? You reabsorb the salt here, so this is always salty. Amazing. See? It's just, there's movement. But this is where we appreciate the word physics, osmosis diffusion. How did that happen? There's difference in permeability characteristics. This one right here is unchangeable. This is always permeable to water only, always permeable to salt only. This is the one that you control with your hormone, antidiuretic hormone, which responds to your hydration status. So when you're dehydrated, antidiuretic comes, open this one, aquaporins, osmosis here, that's when you have a dark PP. You see that? It's amazing. So that's tubular reabsorption. That's how you reabsorb. Okay? Reabsorb. Yes.
So things like Lasix, would they stop basically do they like stop all of the
Lasix? Well, Lasix, that's a very good question. Lasix is furosemide, right? It's a diuretic. So what it does, it doesn't stop the antidiuretic hormone, but it stops the reabsorption of the salt. So you have a high concentrated PP. That's very good. You have other diuretics. You have alcohol, it's a common diuretic. A for ADH. So the target of alcohol is antidiuretic hormone. So as the alcohol goes to the brain, it slows down the release of antidiuretic hormone. So you PP a large amount of urine. How about caffeine? Any caffeinated drinks. Ne for sodium. That's how I try to remember. Caffeine promotes the or prevents the reabsorption of sodium. So you don't reabsorb sodium, you PP a large volume of urine. And Lasix is the same. So, do you have any questions so far? Any questions? Now, look at. It's very easy, isn't it? It's just just remember in the blood vessels, blood pressure. Then here, you remember the word diffusion osmosis. That's all. It just follows diffusion osmosis. And how does that happen? You remember permeability characteristics. That's all. It's very easy. Now we move here. That's how you reabsorb everything. Your glucose, everything now ends in your interstitial fluid. Then how do you move from here to here? You remember your albumin, right? So the albumin is just going to reabsorb all of those precious nutrients. And where is it going to go? Back to my circulation. That's why it's called counter current exchange. This is what you refer to as counter current exchange. See, there's counter, this is going back to you, this is going to your Puget Sound, counter current. They're exchanging, exchange gifts. This is the basic mechanism of how you form your urine and how you have your clean blood. See, that's why I call it Jiffy Lube. There's you filtered out your urine. Don't forget the terms: uh, blood filtrate or what did I say? Tubular fluid, then urine right here, then interstitial fluid. You have any questions? No questions so far? Okay. So the main waste product that we want to get rid of is what you call urea. We know that. That is the main waste product. And there's others, uric acid. They're all mainly from protein breakdown. Protein is the pain. Because we are humans, we do not have enzymes that break down the ammonia. That's the pain. So the only way to get rid of that is through the kidneys. So it's very important then to always assess the health of your kidneys. Remember, look at once it gets to the pelvis right here. In fact, once it gets to the collecting ducts, this one right here, the major calyces, minor calyces, then major, then pelvis, right here is where you call it urine already. So here, all the way down, goes down to your bladder. Are you still forming urine? No more. Which organ did that formation of urine? It's the kidney. So doesn't it make sense that what they do is always evaluate kidney function? And do you agree with this slide? There are two ways to evaluate kidney function. Look at your PP, look at your blood. Because if you didn't get rid of the waste, where is the waste? It's still in your blood. And that main waste product is called urea. So you look at the urea in the blood. That's why it's called blood urea, nitrogen, BUN. So if your BUN is high, isn't that a sign of renal failure? Right? Or they can also use what you call plasma clearance. So what they do with this one, they can use inulin or any other, inulin is the most common, or para-aminohippuric acid also. They inject you with that specified amount of substance. They use either creatinine clearance, heard of that one? But they can do this inulin. So you either ingest it, and it's a specified amount, because you don't make it, you don't reabsorb it. What you put in should be the same amount that comes out in your PP. You can't breathe it out. It should be in your PP. So if there's a discrepancy, you know that there's renal failure. You understand what clearance then means? When you see that creatinine clearance, you should, oh, it's supposed to be cleared by my kidneys. And if it wasn't cleared, it's still in my blood. That's what it means, okay? Can you clear creatinine in your lungs? No. So remember, you only have two exits for your blood-borne substances, kidney and lungs. Now, so you understand this, you understand this one, right? Apart from blood, the most basic and still very useful tool is the urinalysis. That's why you're going to do urinalysis when we see each other again for our lab, okay? What is urinalysis? So you're going to look at the color of your PP. Remember this one. Look at. There will be in your test, maybe it will be the same for you. There will be a section where I will ask you, please let me know or tell me if the following are normal or abnormal. And you want to answer that part thinking about the kidney. Is this value or is this thing telling me that the kidney is working or not? So you see, you say dark, deep yellow urine. That's normal. What that means, or dark your urine. I'm going to write that's normal. It's telling me that my kidney is working for me. I know that means you're dehydrated. Something going on with you. But I also know that my kidney is working. That's how I want you to answer that part. Okay? So, when does it become abnormal? When there's blood. Because you remember, blood should never be in the urine. It's big. It shouldn't be in the urine, especially in males. In females, if you have your period, maybe there can be blood there, right? But never in males. Okay? There should be bacteria in there called pyuria. Oh, I have it in the next one. So, you should know these terms. You should remember what's abnormal. It's not normal to find sugar in your urine. It's a nutrient that you're supposed to have reabsorbed from your tubules. Remember? What you don't reabsorb is the waste. You want to get rid of that. But the nutrients, you should have been effectively reabsorbing them from your tubules. Do you remember? So, glycosyl, it shouldn't be. You should not have glucose in your urine. Here is where comes the word transport maximum. This is why, even if we're healthy, we want to pay attention to the nutrition guide pyramid. We don't want to overload our kidneys. When we have too much glucose that it spills in your urine, okay, the cells right here, the cells that line your tubules right here, is just like, remember what I always use the example of the bathroom, right? If the ladies' room, if every cubicle is filled, do you push in there and you say, can we please share the toilet? You don't do that. You wait for your turn, right? That's the same thing here. Look at. It keeps moving, glucose keeps moving. But then, maybe all the glucose channels are filled, so you're not able to reabsorb some of that, it spills. Transport maximum. You understand what this means? Means the bathroom is full, right? You have to wait for your turn. So, how does this wait for its turn? It goes in your pee. Glycosuria, yes.
Isn't that a sign of diabetes?
Yes! Yes, very good. That's a sign of diabetes. Because insulin should have been enough to tell this glucose to be in your cells. But if there was not enough insulin, there was a lot of them that landed in my tubules, and so there's a lot of them that I have to reabsorb, and so some of them spills because you were lacking in insulin. Make sense? Okay? Okay? So, what are the other terms that you needed to know for your proteins? Make sense? You shouldn't have proteins because that's the law. Well, my law. That the RBC, white blood cells, platelets, albumin, globulin, fibrinogen, they're too big than the biggest pores or openings of your capillaries. So they shouldn't be in your urine. If you have that, do you understand? If we have this, I'm thinking, this one right here, I'm thinking your problem is already in your blood vessels. It's up there. If it's this one, maybe your kidney is still working. It's just you have too much. But this one, for sure, there's a damage in your blood vessels. You damage the glomerulus, which is the site of filtration. Okay? Ketones, leukocytes, pyuria. Usually I give, pop quizzes, so you should be able to define terms for me. What is pyuria? There's white blood cells in your urine. Okay. Other terms you need to know. Polyuria. You don't even have to memorize these values, but if you can, then polyuria means increased urine output. Oliguria is decreased urine output. Anuria is no urine output. So again, don't forget, you're going to analyze that section of urinalysis as to whether does this tell me my kidney is working or not. If there's blood, that's not normal. How about calciuria, meaning calcium in your urine? That's normal. Maybe there's too much. Presence of magnesium, sulfate. What? Okay, that's normal. I'll write rusty brown urine. That's normal. If I write blood, that's not normal. There's sometimes your diet can also give the color of your pee-pee, right? What is it? What vegetable gives you different color in your what is it? What color?
It's green. Drink it green.
Okay, there's one more also that makes it. Anyway, what?
I don't remember.
Some vegetables gives a different color, right? But that's still normal. You see? Okay. So do you have any questions so far? We're done with your kidney. Now we're going to look at the rest. Okay? We're going to look at your ureters, then your bladder, then your urethra. Then we're done. You need another break? No? Yes, tomorrow? I give you 1 minute, 2 minutes break. Okay? To relax. We're almost done. Now, we formed our PP. There's our PP right here. You have any question? Don't overwhelm yourself. The book is very, very detailed. But you just need to remember. What do you need to remember? Blood, there's blood pressure. It can constrict that. But here, what is it? Just concentration gradient. The only way that you move your substances in your tubes is diffusion osmosis. That's it.
So when you have a UTI, is it in the ureters or is it? 'Cause what is
Urinary tract. Very good. Right here. Not
So,
here.
if
When
it-
you have a kidney infection, they will say renal. So you will have a definition, a diagnosis. Pyelonephritis or pyelonephritis, meaning it's the kidney. Right here. Pyelo is right here. Then nephritis is the kidney. Anytime you see the word nephritis, then that means it includes this one. But UTI is just here, yes.
Can a UTI cause nephritis? Can it
Yes,
work its way
of course. We're gonna look at yes. Oh yes. And you're gonna see anatomically how that happens. That's why when you feel the urge to pee-pee, don't hold your pee-pee. I get mad at Lily with the kids because they're like playing or they're doing something. Go right away. You're gonna see why. Yes.
So when someone has UTI and they go septic, is it because of the diffusion?
When someone has UTI and what?
and they go septic from it,
Yeah.
is it because the infection is leaving with the
No.
into the blood when it
Well, when they go septic, what happened is remember what's going. Yes, the bacteria, because we're going to study. There's always germs right here, isn't it? Right here in your bojangles, right? There's always germs right there, right? And look at what's here. This is waste. Like your trash. If you leave your trash for a long time, you see some worms, some maggots in there growing. So that's ideal environment for our germs. So then they start creeping up. That's how they go septic. We're going to see how that happens. Now let's look at. So this is the ureters. And here is where you form your urine. Look at how very good of an architect God is. And there's your bladder. You can guess how will urine move from here to here. Can you guess? Can you give me one? Very good. Gravity. Right? Gravity is one of the key factors that can move your urine from here to here. Another one, hydrostatic pressure. Like the waterfalls, right? Hydrostatic pressure. It just falls down. The waterfalls. And another one, can you guess? The ureter is smooth muscle. So, what's that forward movement like in your GI tract? Very good. Peristalsis. So what's the function of the ureter? It's just for transport of the urine here to here. You cannot afford for that urine to stay here because remember, one round trip, your heart keeps beating every time, 80 beats a minute. So 80 times there's drip, drip, drip. And 80 times there's waste that you need to get rid of each minute. Okay? Now we get to the bladder. I want you to see the bladder. There you go. There's your bladder. The bladder is an ideal holding chamber. So this is where we're able to hold our pee-pee. What are the features of the bladder that helps us to hold our pee-pee, especially for the girls who are so picky? The bathroom is stinky, so I want to wait for the next one. I'm going to hold my pee-pee. How does it do that? Number one, remember, this folds rugae. You remember rugae? What is rugae? Temporary folds. So when you open the bladder, just like the stomach, cut it open, stretch it. It will be stretching smooth. But normally it's wrinkled like that. Rugae. Number two, I'm sure you remember this one. Transitional epithelium. Remember where it can transition from many layers to a few layers. That helps in expanding so you can hold more urine. Number three, you remember smooth muscle? The plasticity of smooth muscle, right? So these features make your urinary bladder ideal for storage of pee-pee. You know when the bladder expands to about 400 mils amount of urine there, that's when you feel the urge to pee-pee. When you feel the urge to pee-pee, go banyo. Banyo means bathroom. Why? Look at this opening to the bladder. So there are three openings here. Two from the ureters, one to the urethra going out to the Puget Sound. Look at this opening. Look at what it says. It's not anatomical, a physiological valve only. Why? It's just like the valves of your veins. Look at this. It's just modified fold of what? Epithelium again. Do you see any chordae tendineae holding it? No. It's just a flap like that. A soft flap, not even connective tissue. So what does that flap mean? It can be a swinging door, right? So yes, it can prevent reflux, but not effective. That's why when it feels to 400, you feel the urge. If it's effective, you won't feel the urge. But you feel the urge. It's telling you, go empty it. Because why? Because it easily can revert like that. And what happens? Up, up, up. So you're not concentrating, but you're holding on to waste. That's ideal environment to the bacteria right here in the vaginal area. See? So they like that. They grow, 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 grow. Go up, 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 up. You understand? So I remember that was asked in the test. Why is it not good to hold your pee-pee? What is it? What is the anatomical explanation? You're going to say, these ureteral valves or openings are not true valves. Yeah, I think that's why they write openings now. They don't write valves actually. To make sure that we grasp that fact that this is not a true valve. It's just an opening. So when you feel the urge, you need to really pee. You will see what will happen. Some of you will have what you call casts. Can you imagine? So when you held your pee-pee, you understand that you held your pee-pee. In the meantime, it should keep dripping. But then this is getting full. So what happens? They're slowing down, right? they're slowing down. You're forming a line because they're out, right? You start forming a line as you wait to buy your tickets to the movies, let's say. So when you're forming a line right here, you're going to start forming casts. Like if your crystals or your fats right here, whatever, they start forming casts or assuming the shape of the tubule where they were. So when we do our microscopic analysis, you see a cast, a big clump, they're clumped together, casts. When you see casts, does it make sense? That's a sign that you were holding onto your PP for a long time. That's not good. You don't want to see all those casts or all those crystal sediments. You want clear PP. You understand? Okay. So this bladder, why is it very good in emptying? Why does it help? This bladder, the wall of the bladder, the muscle is called detrusor muscle. It's very powerful. It has an innermost oblique muscle. So it has many layers of muscle, inner circular, outer longitudinal, and an innermost oblique, which is very good in emptying your bladder. So powerful contraction. Okay? So the next step is to pee. Peeing is called micturition or urination. Urination is called micturition. Micturition. And micturition is a reflex. So when your bladder gets filled to about 400 mils, of course this one stretches, right? And the mechanoreceptors triggers a reflex, a sacral spinal reflex. See, S2, S3, S4, and it's a reflex. And this reflex promotes contraction of this one and relaxation of this sphincter here. So this bladder, look at this bladder empties or ends right here, and this is the beginning of your urethra. There's two openings that guard the urethra. The first opening is called the internal urethral sphincter, and the internal urethral sphincter is nothing but the most inferior part of your bladder, so it's smooth muscle. The external urethral sphincter is in the perineum. And the location, so the perineum is this part right here, right? And the perineum, the location of the perineum is the same for both males and females. That's where it is. So what happens when you have the micturition reflex? The bladder stretches, the reflex tells the bladder to contract, and the internal urethral sphincter to relax. But the external urethral sphincter is voluntary. So what do you do when you pee? Don't you go increase pressure also? Here is pressure. You want to push it out. You want pressure. There is a difference between male and female urethra. You know that, right? The male urethra, which is this one, is both a shared organ between your urinary system and your reproductive system. The female urethra is just uniquely or mainly an organ of your urinary system only. Where is the external sphincter? For females, right here. For males, it's right there. It's not here. That's why I think it's so funny how some boys, when they try to control their PP, they're squeezing this one, preventing. It is the external sphincter is not there. The external sphincter is right here in the perineum. Okay, so then you PP out, you're done. It's out in the Puget Sound. So some problems, incontinence. If you cannot control your micturition or your PP, then that's called incontinence. The reflex, you know, it has to be develop. So babies, they are not able to control it yet because you have to have the proper neurological connections. So by 2 or 3 years old, they should be potty trained. If not, then they are incontinent. When you get older and maybe you have a stroke, then you can have incontinence. So it's called neurological incontinence or stress incontinence, which is very common among females. Because the external sphincter is a skeletal muscle, you can strengthen that. What do you call it exercise? Is it Kegel exercises, right? So there's some exercises to strengthen that sphincter. It's a sphincter. And when you strengthen that, then you can, hopefully it will help you control your pee. But it's a natural consequence, especially among females with multiple childbirths, because it just stretches that sphincter. You have any questions? You're done with your urinary system. See? It's very easy. Now you understand why. I hope you appreciate the importance of going to the bathroom. You need to go to the bathroom. If you don't go to the bathroom, the pee stays here. And that's when you start seeing some crystals. Can you imagine the crystals scraping the bladder? There's going to be blood. So that's when you will see blood in your pee. Okay? And remember, you see how your kidneys, remember it follows the concentration gradient right here, diffusion, osmosis over here. Do you see now? I told you it's an automatic thing. You see, water, aquaporins, it's an automatic thing. It's beyond your control. So if you have a lot of substances to get rid of, it's beyond your control. You gotta drink water if you eat too much protein. Okay? Do you have any questions? I think